to all and welcome to this lecture. We are in module 9, lecture number 2, which is charge sharing part 2. In this lecture, we will discuss about halo implants, the impact of charge sharing in narrow width devices and some limitations of charge sharing model. These are the learning outcomes of this lecture which help you to understand the charge sharing effect in narrow width devices. It will help you to understand or differentiate the narrow channel behavior in two different technologies, like one is STI and another is low-cos. This lecture will tell you about the modeling limitation when we incorporate the charge sharing effect in our long channel models. So let us get started with a quick recap. In previous lecture, we have discussed about the charge sharing effect. We said that when the channel length is small enough, then the source and drain shares the charge. It means it reduces the effort applied by the gate to deplete the channel. We have extensively discussed about what is the portion shared by the gate only, and then we have decided that QB1 cap is the total gate charge which is shared by the gate, and the rest of the charge is shared by drain and source. We have calculated that QB dash 1 cap by QB is less than 1, meaning the channel charge which is shared by the or which is controlled by the gate is lesser, and hence the body effect is lesser than the body effect of the total channel, which means the threshold voltage is reduces. So the charge sharing effect is a severe effect in short channel devices, because in this condition the gate loses its control. We have derived the expression for ratio of QB dash 1 cap by QB, which is in the form of some parameters like junction depth, depletion width thickness, channel length, etc. We argued that when you increase the VSB voltage, then depletion region thickness increases, and hence the sharing of charge provided by the gate will reduce, which will actually reduce your gamma 1 cap per gamma. That means the threshold voltage will reduce. So that is all about the charge sharing model when we were talking about small channel length. But what will happen? But now we argued that we need to have some solution to reduce down this threshold voltage. It means to hinder the reduction in the threshold voltage when you go for small channel devices, because ultimately the reduction in the threshold voltage or the threshold voltage roll off results in higher leakage. One of the possible solutions is incorporating or including halo implants. So again, to see the charge sharing effect, you can see that you do have a junction here N plus NP. In the N plus P junction there will be a depletion region, and this depletion region does have a significant width when your channel length is very much small, and the contribution of this depletion region is actually causes charge sharing, which reduces the impact of gate. Now to increase the threshold voltage, you need to increase the gamma or increase the body doping. So one solution is I can increase the substrate doping, but if I increase the substrate doping everywhere, then the body effect coefficient of the device will increase. Thus what can be a possible solution? As we have discussed that this charge shared by the source and drain near the surface can be ignored or can be mitigated by providing some local doping here. That is what is called halo doping or halo implants. This can be done by using ion implantation, where what we do in near the source and drain region we will provide a heavy doping, but the rest of the channel is only p type semiconductor, where here it will be P plus. P plus means what? The doping will be higher. Now when you apply a proper biasing, then the depletion region expands, but because of heavy doping, the expansion of the depletion region in the channel is less, meaning the expansion of the depletion region stands for dB. So, the dB will be less because in previous lecture we have seen that it is 2 into epsilon divided by q into Na into phi naught. So, if you increase Na, the expansion of the depletion region is less, and hence the charge sharing effect will be reduced. Now, if you provide a halo pockets or halo implants near the source end, and when you increase the voltage, then this depletion region comes closer to each other, correct. If you increase the voltage to a very high value, and if the channel length is significantly small, then what will happen? The pockets depletion region will touches to each other, and hence the overall doping here will be very high, which is P plus. Thus, the gamma of that region is locally increased, and hence the threshold voltage shows a increasing trend. So, there will be abrupt rise in the threshold voltage, which was decreasing in the channel length. However, because of this halo implants, we increase the threshold voltage. This kind of effect is called reverse short channel effect. Reverse short channel effect. Now, if the depletion region thickness is comparable to the overall channel length, right, then again there will be find a decrease in the threshold voltage. So, halo implants or including the pocket dopings is one of the possible solution to reduce the short channel effect, which was introduced by charge sharing. Halo implants means locally increase the substrate doping, which actually limits the depletion region spreading, which actually reduces the charge sharing and suppresses the threshold voltage roll off in small channel devices. Now, in modern CMOS technologies, which is rely on halo implants to control the short channel effects, especially in high performance devices. Strictly speaking, the modeling of charge sharing effect is essentially required when there was no halo implants, because halo implants is not providing that much short channel effect. We need to be modeled and considered in terms of charge sharing. So, there is another kind of charge sharing effect in narrow channel devices, meaning if I draw a MOSFET like this, this is N plus, this is N plus, this was the channel length between source and drain, but this is a 3D structure. So, if I go like this dimension is width dimension, right. When you apply the gate voltage in this region, then the depletion region forms beneath the gate, and now when you change the width of the device, then how the charge sharing effect come into picture, we need to model. That is what here we are using subscript 2. 2 means the second charge sharing effect we are considering. So, what will happen? Ideally the gate field line should go vertically and causes a depletion here, but in principle the vertical field lines will, the field lines will not exactly vertical, but they are having some curled shape. These field lines are called fringing lines, fringing fields. Now, what will happen if these lines are coming at this section? So, ultimately these field lines will also support the depletion of the channel, correct. It means if I will represent in terms of effective capacitance, then you see the effective capacitance of this region will increase, correct. In the sense the total capacitance which is shared by the gate will increase, and if I go back to our basic equation of threshold voltage, then we will find that Vt is equals to V flat band voltage plus phi naught minus Qb by Cox, meaning if we are not considering charge sharing effect, then the charge which is shared by the gate is due to only vertical field lines, and we need to only consider these capacitance, which is nothing but oxide capacitance per unit area into width into L. So, this will give me the total capacitance, which is oxide capacitance. However, when the width of the device is shrinked, then these fringing lines will be significant, and hence these fringing lines will additionally deplete the channel. Thus, the oxide capacitance will increase, or the effective capacitance seen by the feed lines of the gate will increase. So, I can rewrite this as COX cap, where COX cap represent the increase in additional capacitance. And if we go back to find out what is the effect of this increase in the effective capacitance shared by the feed lines in body effect coefficient, then we will find gamma 2 bar by gamma 2 is equals to COX divided by COX 2 cap. So, if the capacitance, sharing capacitance by the field lines, gate field lines will increase, then gamma 2 cap will be smaller than gamma. Ultimately, this will reduce the threshold voltage. Again, for physical understanding, you can think like 100 field lines are coming from the gate, but additional these 3 or let us say 10 field lines which are coming from the gate will also causes the depletion. Thus, the overall effort by the gate is reduced, and hence the threshold voltage will reduce. That is what, if you reduce the width of the device, then you will find that there will be a threshold voltage roll off. It means for a very narrow devices, the threshold voltage will reduce. We can simply relate the ratio of COX per COX cap in this STI process, where STI stands for shallow trench isolation. In shallow trench isolation, we actually provide the boundaries of oxides, right, and hence the depletion region will form only beneath the gate. But additionally, these capacitance or additionally these feed lines from the side, which is called fringing lines, will deplete the surface, correct. So, that is what we are actually calculating, the ratio of COX per COX cap. If you calculate the overall capacitance of the gate without considering fringe lines is COX cap into W into L, and when you consider the capacitance of fringe, then it will be COX cap into W into L plus CF double dash. Here CF double dash is the capacitance per unit length, not per unit area. Meaning, if you see closely, this is the region which we are talking about, below which the depletion region forms, correct. So, along the width, the fringing field effects is not there. However, along the length, the fringing field lines will be there, and ultimately it will deplete the channel. That is what we need to define an additional capacitance per unit length. So, the unit of this capacitance will be farad per micrometer or so, right, and hence multiplied with L. This will give you the overall capacitance, but we need to multiply with factor of 2 because this will happen at both the sides. So, you can simply go and see this picture from this side and this side, there will be a fringing lines, correct, and hence you can solve this ratio as COX by COX 2 cap is equals to 1 over 1 plus 2 CF double dash divided by COX into 1 by W. Now, if I find what is the ratio of fringe capacitance per oxide capacitance, consider there is a C capacitance. So, C into L divided by C into W into L, right. The overall capacitance considered is C. So, ultimately you will find the ratio is inversely proportional to W, meaning what? If you increase the width of the device, the effect of fringe capacitance is very small, and hence you can simply neglect. However, when you reduce the width of the device, the ratio of fringe capacitance per overall capacitance will increase, or the impact of fringe capacitance is increases. That is what you cannot simply ignore that part, and you need to consider that part. That is what we call charge sharing effect in narrow width devices. The another approach to understand this is LOCOS process, where LOCOS stands for local oxidation of silicon. This LOCOS process is basically used in high voltage integrated circuit. What is the idea? A very layman idea of LOCOS process is, suppose I do have a MOSFET like this, and this is an oxide beneath which I am making our MOSFET, and there is another MOSFET in the chip, and I want to isolate these two MOSFETs. So what we'll do, we'll create a isolation thick oxide, right. So let me make like this. So this is an isolation thick oxide, correct. In general, we can take some nitride layers as Si3N4, right. So if you see from the width side, you will get this kind of structure. So one is an oxide, gate oxide, one is an isolation spacer or isolation oxide, and another is gate oxide of other transistor. However, when you go for oxidation, meaning oxidation either using O2 or H2O, then this oxidation is not exactly vertical. It means it penetrates somewhere in this isolation layers, and hence you will get this kind of structure, correct. Similarly, here this kind of structure will come like this. If you see carefully, this region is somewhat similar as bird beak, it is like this. So that is what we use term bird's beak structure, right. In this process what happens is, if you see carefully, if you are applying the gate voltage from here, the job of the gate voltage or the field lines which are coming from the vertical side, it is not only to deplete the channel which is beneath the gate oxide, however, it should deplete or it will deplete this side of the channel also. It means now the gate voltage is doing extra effort to deplete this side, correct, and hence the threshold voltage will increase. Let us see how we can incorporate this charge sharing effect in terms of equations. So again here we are defining a subscript 3. So this is a third charge sharing effect we are discussing. First one was charge sharing due to small channel length, the second was due to STI process, and third is due to LOCOS process. So what happens is, as we said, that because of this bird beak structure, the gate should do an extra effort. It means if you are having gate here, ultimately these field lines will deplete this region as well as it will deplete this region. It means what? The ratio of QB3 by QB will be greater than 1, because the QB3 cap is the overall charge which is shared by the gate or which is controlled by the gate. Now you see the area or the charge which is controlled by the gate is increased, and hence QB3 by QB3 cap by QB3 will be greater than 1, which we can incorporate here in our threshold voltage equation, which simply says V flat band voltage plus phi naught minus QB3 cap per Cox, correct. And as this is increased, the gamma 3 will also increase. So gamma 3 cap is can be written as QB3 cap per QB into gamma. So if this ratio increases, gamma 3 cap increases, where gamma is nothing but body effect coefficient, and hence the threshold voltage increases. That is what you can see. If you reduce the width, then after a certain limitation the threshold voltage increases. This is just opposite which is we found in STI process. Now how can we calculate this QB3 by QB ratio, as we have also done in our previous analysis on STI and short channel effect? Then let us do some simplification. With this bird's beak view, I am just considering, so if you just closely see, this will look like this, right. because there is another bird's beak structure coming in this side. So if I just observe this region, I am considering the top region of the silicon is just flat, correct. So you can simply see, assume that there is no bird's beak effect, and thus the silicon surface is flat, meaning for the simplification we can simply say this is the top plate. Now top plate of the oxide, right, or top side of the oxide. Now the next is, instead of making bird beak, we are just making a small circle here, right. This is an ideal picture. Practically you can simply relate as a bird beak like this. Again you can find this a bird beak structure coming up. So we are talking only about this red part, and we will calculate what is the total QB3. If we see closely, this is QB, or this should be QB. This should be the charge which should be controlled by gate. However, in low-cost process, this is the additional charge which is controlled by the gate. So QB is nothing but what? Width into this dB. So QB is width into dB into, yes, some charge. However, QB3 cap is W into dB into Q, which is nothing but this rectangle, plus we do have some regions which can be represented by some portion as the circle. If you consider this as a radius, right, then this circle is nothing but 1/4, 1/4 of a circle into pi dB square, correct. So this will give you the area of this shaded region, and it is two sided, right. So you need to multiply with 2. So ultimately the overall charge you will get as W into dB into Q into 2 into 1/4 into pi dB square into Q. Now if you calculate the ratio of these charges, then you will ended up as QB3 cap by QB is equals to 1 plus this 2 and this 4 get cancelled, ultimately you will get 1/2 pi, this dB and dB will get cancelled, dB by W. That is what written here. So ultimately your charge sharing effect in low-cost is also dependent on dB and width. If dB increases or the depletion width increases, then your charge sharing effect increases and hence the threshold voltage increases. Similarly, if you reduce the width, then charge sharing effect will become more severe. Now we will see what are the possible limitation of charge sharing models. In general, the charge sharing models improves the long channel theory. However, it cannot fully capture the short channel effects, because we have assumed few physics which we derive for long channel is hold good for short channel, which is not true. As I mentioned that the equation Vt is equals to V flat band voltage plus phi naught minus QB dash per Cox dash. This equation was derived from the assumption that only one dimensional analysis is true. However, in short channel devices 2D analysis needs to be done, and hence this equation does not hold good. The major limitation of charge sharing model is it is only capturing the effect in threshold voltage, which means if we consider the charge sharing effect and included in the threshold voltage, it will only show the shift of the IDVG characteristic in horizontal axis. So let us consider if it is VGS, this is IDS. When you plot this curve, this point is threshold voltage. So we defined as Vt plus alpha into VDS divided by 2. Now if some charge sharing effect is there, then you can say because of charge sharing my threshold voltage is reduces. So nothing but this graph is shifted like this. So whatever we modeled based on charge sharing, it is only shifting the curve in the horizontal axis. However, because of charge sharing, as the two-dimensional analysis comes into picture, the behavior or the trend of these graphs is also changes, which is not captured by the charge sharing models. So this is basic limitations of charge sharing models. So let me summarize this lecture. In this lecture we said that the charge sharing is a severe effect which actually alters the threshold voltage. The best way to incorporate the charge sharing effect in our long channel models is to include through change in threshold voltage. We find that the change in threshold voltage is represented as Vt cap, and we have discussed that in long channel devices the threshold voltage was given by V flat band voltage plus phi naught plus QB dash minus QB dash by COX. So when you go for short channel devices, then charge sharing effect will come into picture, and this COX or QB will be changed. Accordingly, we need to find out how the gamma is changing, and accordingly threshold voltage given by V flat band voltage plus phi naught plus gamma times of square root of phi naught plus VSB changes. In this lecture, we discussed that one of the possible solution to reduce the charge sharing effect is halo implants. We need to create some local doping near the source and drain with a higher doping concentration, that is P plus. This will help us to reduce the depletion region spreading in the channel, and hence reduces the charge sharing effect. We have also discussed about STI process and Locos process, how these process causes the charge sharing effect. We derived a basic equation considering the ideal effect and without considering the bird's beak structure, such that we can relate how my charge shared by the gate over total charge is related with the depletion thickness and the width. Correct? So we will stop here for today. Until then, take care.